Hello, this is Russell from the Tate Geological Museum, and today I'm going to be talking to you about meteorites, a subject that's near and dear to many hearts. Meteorites are basically rocks from outer space. They fall to the earth in the form of meteors, shooting stars, and after they've hit the ground and are lying on the earth, then we refer to them as meteorites. So that's just two different words for what is essentially the same thing. We just call it something different depending on whether it's still falling through the air or whether it's already landed. Now, of course, one of the biggest questions that people have is how do you recognize a meteorite? And it can be tricky. Almost anybody who finds a dark, heavy rock on their property brings it to us sure that it's a meteorite, and we've had to disappoint a lot of people informing them that they aren't. But there's a couple of things you can look for. Magnetism is one. Real meteorites are almost always magnetic. Now that's not a slam dunk because there are other minerals that can be magnetic as well, but it can at least narrow it down a bit. Something else to look for on a true meteorite are regmaglypts. As they streak in through the atmosphere, they get very, very hot, and the volatile elements that are in there with the rock and the metal will explode off of the falling meteor and leave behind these scoopy bits. That's not the technical term, but it's easier to remember than regmaglypt. So those scoopy bits, you see them here and here and here, those are regmaglypts. And those help identify this as a true meteorite. And they formed as it came down through the atmosphere on its way to the Earth. Now, there's many different kinds of meteorites. Some of them contain more stone, some of them contain more metal, some of them are a mixture of the two, and all of those categories have names. There's the nickel-iron meteorites, the carbonaceous chondritic meteorites, metallic iron, stony meteorites, etc. But if you've got a metallic meteorite, one that's composed almost entirely or entirely of metal, there's another really surefire way to identify it. That is to cut it in half, polish the cut face, and then etch it. And that etched, polished surface will show a pattern of diagonal lines crisscrossing each other. And that pattern of diagonal lines at this angle is called the Widmanstätten pattern. And no process on the Earth, either natural or man-made, can create the Widmanstätten pattern. It's only found in meteorites. So if you can find that pattern on your specimen, that's a slam dunk. You know you've got a meteorite there. Another kind of meteorite, and I think my favorite, from at least an aesthetic sense, is the palisite meteorites. And that's what you're looking at right here. This one, of course, has been cut and polished, and as you can see, it is made entirely of metal. The most common metals in meteorites are iron and nickel, but there's actually also a lot of other metals as well. Platinum, gold, iridium, aluminum, cesium, titanium. If people ever get out to the asteroid belt and start mining asteroids and getting these metals for industrial purposes, they're going to make a fortune. There's a fortune waiting out there. So what's these green things that are like olives in a meatloaf? They are crystals of olivine. And so that mixture of green olivine crystals with that very silvery mix of nickel and iron is what identifies this as a palisite meteorite. Just lovely. And another type of rock that's not actually a meteorite per se, but which is associated with meteorite impacts are these guys right here, tektites. When a big meteorite hits, it hits so fast and so hard that it releases an enormous amount of kinetic energy. As you recall, kinetic energy is mass times velocity squared. So if it's big enough and it's moving fast enough, a lot of energy is going to be released all at once. In the case of a big meteorite, greater than the explosion produced by an atom bomb. And that heat and energy is enough to melt rock. The globs of melted rock fly through the air, and they cool and they harden, and then you get these tektites. Since the most common rocks in the crust of the earth are the silicates like feldspar and quartz, as these melt and then re-solidify, they form glass. And so tektites have a very high glass content. A lot of them are almost 100% glass. So there's an example of a tektite, and here's a few others right there. And one more thing that you might be wondering about, you might be asking, why is there a triceratops in our meteorite display? Well, the reason is that when a meteorite is in outer space, we've got a different name for it. We call it a meteoroid. And meteoroids can come in all sizes, all the way up to about 100 meters across. But if a meteoroid is greater than 100 meters across, we've got a different name for it. We call it an asteroid. And asteroids get from the 100 meter across lower limit cutoff point all the way up to almost the size of Pluto, and every size in between. A very, very large asteroid hit the Earth about 65 million years ago, and that's why Triceratops is no longer with us. It created an enormous explosion, changed the global climate, and killed off the dinosaurs, including the last of them, like Triceratops here. Dinosaurs had ruled the Earth for 190 million years prior to that. The greatest dynasty of large land animals the world's ever known, and all it took to knock them off was a rock from outer space falling to the Earth. And they didn't do anything about it. Of course, they only had a brain the size of a walnut. But what's our excuse?